you to my collaborators. This is Fangzhu Zhang, who thankfully goes by the name Arthur. He was my graduate student and recently moved to Hebrew University in Jerusalem. Go Ogia, who is a postdoc at the Observatoire Côte d'Azur in Nice, working with Oliver Hahn, and Andy Burkert, who is at Munich. So why do we care at all about dark matter substructure? Well, from my personal point of view, I'm interested in halocupation modeling. I try to understand what kind of galaxy belongs to what kind of dark matter halo. And at that point, we believe that satellite galaxies are the galaxies that live in dark matter subhalos. So the abundance and demographics of dark matter substructure is directly related to that of satellite galaxies and to small-scale clustering. So if you want to understand and model small-scale clustering, you need to understand the properties of dark matter substructure. Subhalos also cause flux ratio anomalies and time delays in gravitational lensing. It's actually one of the best ways to probe substructure in dark matter halos. They can heat stellar disks and tidal streams. Okay, other ways in which you can probe this substructure, has interesting dynamics. It boosts the dark matter annihilation signal. If we ever are going to measure dark matter annihilation flux, we want to turn that into a constraint on the mass of the dark matter particle and the dark matter annihilation cross-section. In order to do that, we need to know something about the clumpiness of the dark matter. Okay? And that is basically described by this boost factor, which just depends on the amount of substructure. In addition, this substructure allows us in principle to test the nature of dark matter. It's where we are sensitive and we can tell the difference between CDM, warm dark matter, self-interacting dark matter, and whatever other dark matter there is. This is, for example, an example from a paper from the Durham group, Bosey et al., showing you the subhalo mass function in blue for a typical CDM cosmology compared to what you get if you assume that the dark matter is warm, has a 3.3 keV thermal mass. Then you get the red line. And you see that they start to deviate, okay, at the low mass end. And that's basically because of the free streaming that happens to these warm dark matter particles. And in order to be sensitive, you need to basically go to halos below about 10 to the 8 solar masses. That's where the difference becomes appreciable. Now, 10 to the 8 solar mass is problematic because that is really low mass halos. Reionization tells us we don't really expect much of galaxy formation in such low potential wells. So how are we going to detect those 10 to the 8 solar mass halos? Well, there's different ways. You look for the dynamical effects, for example, in gaps in stellar streams, or I think more promising is gravitational lensing. And I'll show you one example where I think this is really going to be yes, this is because of artificial fragmentation that happens in the warm dark matter simulations that you have to correct for. Initially, people thought that when you go to glass initial conditions, that goes away, but it doesn't go away. There's still artificial fragmentation, so that's what this thing is. Numerical artifact number 1. So here's an example of a gravitational lens. Okay, you see a beautiful lens. Okay, it has substructure. There's 4 galaxies. This is the main galaxy, 3 satellite galaxies. There's a beautiful arc from a background source, and galaxy 4 happened to lie just right onto this arc. And you can see that its mass distorts the arc. So even if there was no galaxy there was just the halo, but the halo had no galaxy in it, you would still see that distortion. So by looking for distortions in these arcs, you can actually probe the amount of substructure. And people like Simone Veggetti have done really marvelous work on that. The problem is that with these thicker optical arcs, you don't have good sensitivity to probe really small mass halos. But with something like this, you do. This is a marvelous example. This is a radio jet that has been lensed and turned into a beautiful razor-thin arc, 3 milliarc-second thick, observed with VLBI by John McKean and collaborators. And you see there's no obvious distortion at all along this beautiful arc. And that means you can actually put constraints on how much substructure is down to about 10 to the 6 solar masses. The constraint at the moment is not very constraining because the total length of the arc is not particularly impressive. But if you get more and more of these systems, you can actually start to do interesting cosmology. The upshot, though, is that numerous astrophysical applications require accurate predictions regarding the abundance and demographics of dark matter substructure. So how can you make such predictions? There's basically 2 approaches. Either you say, okay, we're going to use a semi-analytical model. Okay, and that basically consists of the following steps. You construct a merger tree. The merger tree of the halo describes when each halo accretes all its subhalos, okay, and what the masses are at accretion. And then you integrate the orbit of these subhalos as they move in their host halo, and you treat effects like tidal stripping, tidal heating, and dynamical friction. Or you try to treat that. The pros are this is fast, It's flexible. What I like is it provides insight. You can just, in a model, turn off tidal heating, for example, and see what effect that has. So you get some real cool insight. The downside, though, is that, as I will show you, that the treatment of tidal evolution, okay, this tidal stripping and tidal heating, is approximate at best. You simply cannot write down proper analytical derivations from first principles. And that means you're left with something that you have to calibrate against simulations, which is the other technique, which basically means you run, ideally, a cosmological simulation. Then you need to find the halos and the subhalos. So you run a halo finder. And then if you want to do the dynamics of these subhalos, you need to link the halo catalogs at different outputs together so you can trace things. And that means you need to make a merger tree from your halo snapshots. The pros, of course, is this is in a proper cosmological setting. If you do dark matter only, all the relevant physics is included. It's called gravity. Okay? It should all be there. And the cons are, though, that halo identification is not a trivial thing. Okay? You can give the same simulation to different people, and they run a different subhalo finder, and you will get back different halo catalogs, and they can be substantially different. Okay? This is often not appreciated. In addition, you have a simulation, and a simulation is just that. It's only a simulation. Okay? And it is subject to all sorts of numerical artifacts. And that's going to be most of the talk.
Why do you care about subhalo identification? You have all the data there. Why do you care about some arbitrary method?
That's a very good question. And maybe the field should stop caring about halos. I mean, most of my time, my day is spent trying to convert from one halo mass to another, because 20, 30 years into this field, and everyone has its own definition of halo mass. And I agree with you. In principle, we should think about smarter ways. But this is, what people do standardly. So in this respect, about the numerical artifacts, it's important, especially for the younger grad students in the room, to realize that it wasn't until 1997, 1998, that we didn't even see any substructure simulations. Back in those days, when you ran a simulation, dark matter halos with fluffy blobs without any substructure. Okay? And there were two arguments. When people said, well, this is not consistent with observations. If I look at a coma cluster, I see a wealth of substructure. Why doesn't my halo in the simulation have that substructure? And the one approach was to say, well, that's because we didn't include the baryons. Once we include the baryons and dissipation, you make these dense things, and we'll see the substructure come out. But there were also other people who said, no, but maybe there's something wrong with the simulation itself already. Okay? And there's overmerging. So this became known as the overmerging problem. And people wrote a whole slew of papers on trying to explain what could cause the overmerging. And unfortunately, the field was very confused. Okay? There were people like Halberg and Van Kamp who argued that what is going on is that you actually have collisional two-body heating between the cold particles of the subhalo and the hot particles of the host halo. And when these hot particles fly through the cold halo, and I'm quoting their paper now, this will basically boil the cold subhalo into dissolution. And if you actually do the calculation and you see what it is, you can clearly see that they made an error of about a factor 100, and the effect is actually not important. A slightly different approach was made by Van Kamp, who said, no, it's not a collisional effect. It's actually a collisionless effect. It's just tidal heating, because your subhalo is moving to this host halo, but this host halo is artificially modeled by massive particles that are 10 to the 9, 10 to the 8 solar masses, because you have poor resolution. So it's like a subhalo moving through a sea of massive black holes, and that will tidally heat and distort my system, and that will cause the overmerging. And again, if you do the calculations, you can actually show that it's not relevant. What is relevant is the point that was made by Ben Moore, and that's that you just have too few particles. And when you have too few particles, what you end up doing is you take a softening length that's too large, and that makes your system too fluffy, and that's why it disrupts. And indeed, a few years later, in 1997, Beppe Torman was the first to run a simulation with enough resolution that suddenly he started to see surviving substructure. And very quickly, almost overnight, we went from talking about overmerging problem to a new problem, the missing satellite problem. Because what they found was if you run a simulation of a massive cluster or a Milky Way-sized halo, they looked self-similar in the dark matter. But if I look at a coma cluster and the Milky Way, it doesn't look self-similar. We have too few satellite galaxies in the Milky Way. That was the point. That's why it became known as the missing satellite problem. And hundreds of papers have been written on this. But to me, this has always been a puzzle, because back in 1980, we already knew that the halo mass function is steep and the galaxy luminosity function is shallow, and that means that galaxy formation becomes inefficient in low mass halos. And therefore, even if there's self-similarity in the dark sector, it doesn't mean it looks self-similar when you look in the light. Okay? And that basically is the problem. This problem is basically explained by galaxy formation, baryonic stuff. Yeah, and those papers never got published. He was trying to argue that it's still overmerging in the simulations. And in that respect, he actually was right. Okay. But it's a good point. This paper never got published. I actually don't know why. I think maybe because they were actually not entirely correct. So what people do nowadays, so people stop talking about overmerging, but it doesn't mean overmerging has gone away. So what people nowadays do is they run resolution studies. So they run some simulation, and then they run the simulation at somewhat higher resolution or somewhat lower resolution, and compare subhalo mass functions between the high and the low resolution. And if you do that, you always find that if you go to higher resolution, your subhalo mass function suddenly extends down to lower masses. Okay? That's nicely shown here. This is from a paper that I wrote with Arthur last year. So these are subhalo mass functions. Just look at the upper panels. This is in the Bolshoi simulation, which is the high-res simulation in this case, compared to multi-dark, which is just a larger box, same number of particles but larger box, and therefore lower mass resolution. And you compare the subhalo mass function and the host halo masses in 3 different bins, and you see at the massive end they nicely agree. Okay? And these people say, we have converged. Okay? At the massive end we can trust the simulation results, but then suddenly here you see this turnover, and that happens at this green line roughly, which corresponds to 50 particles. Okay? So this here corresponds to 50 particles in multi-dark. And if you look at where's 50 particles in Bolshoi, that's here, and again you see this turnover. So based on these kind of studies, these people argue, okay, our simulations have converged down to 50 particles per subhalo. And you can go into the literature and look at what people have written about that, all these people who simulate for a living. Okay. Subhalo mass functions are typically converged down to n of about 100, 50, 100. Okay. Subhalo velocity functions, if you want to make a function of Vmax, okay, which is the maximum circular velocity, that actually probes inside the halo, and therefore you need to actually resolve the halo, which requires a little bit more particles, so it's typically a few hundred particles. Only last year, Anatoly Klipin wrote a paper saying the error in Vmax, if you want to have the error in the maximum circular velocity less than 2%, then you need to tune your softening length to this particular range. He said if your softening length is larger than 0.3 rs, your halo becomes too fluffy and you can't measure Vmax properly anymore. But he argued, don't make it much smaller than 0.1 rs, because then you get two-body relaxation effects. You want to avoid that. I'll talk more about softening later. Other thing that people have done is say people use subhalo abundance matching, which is a sham, but that's what they do. Yeah, that's fine. I know. So basically the idea there is that you put galaxies in halos, and then you can make a computer correlation function of galaxies. And people have asked, down to what masses of subhalos do I get convergence in that correlation function prediction? And Klipin argued, all you need to do is use all subhalos that at accretion have more than 150 particles. Okay? Gould and Simon White said, be a little bit more careful, at least 1,000 particles. The upshot is, if you look at any of these numbers, they are low. You're going to make me believe anything that's similar with 100 particles? Even 1,000 seems, okay, a bold thing to do, but this is what the field does. Okay, hundreds and hundreds of people have written on this subhalo abundance matching, and they're using these halos to make predictions for the clustering and to constrain cosmology, and God knows what else. So I decided I want to understand this a little bit better. I want to understand how well we can actually understand subhalo evolution. And I started to study subhalos in an existing simulation, in particular in the Bolshoi simulation. So the Bolshoi simulation is a box size of 250 megaparsecs, 248 cube particles, a sort of state-of-the-art cosmological simulation. The nice thing is the halos and subhalos have been identified with a 6D phase space finder, halo finder, okay, called Rockstar, which was developed by Peter Baruzzi. And this is really cool because a lot of halo finders that people use, even today, things like SubFind, it's very popular, just identify halos in configuration space. Okay? And it's really hard to do. In 6D phase space, you will see a subhalo, just a coherent blob of things moving in one direction. It's much easier to identify subhalos, in particular, with a 6D phase space finder. Then he constructed merger trees, so you can link all these halo catalogs together with a merger tree that he constructed using what is called consistent merger tree code, that also was developed by Peter Baruzzi. And all of these things are publicly available, which is good for people like me, because you can just download them and play with them. And I last year, or a few months ago, weeks ago, submitted a paper, okay, it's an SRPH, in which I study the subhalo evolution in great detail in this simulation. And I just wanted to highlight two results from that. The first one is related to the mass evolution of subhalos. And before you go and do anything, you always have to ask yourself, what do I expect? Okay? So what do I expect how the mass of a subhalo evolves over time? And it's sort of shown here. This is from an analytical study by Taylor and Baboul, 2004. This is the mass as function of time, okay, for a subhalo as it moves around in the halo. And the idea is every time it has a pericentric passage, you strip off a new layer of mass. Okay? And that's why you get a sort of a staircase-like behavior. Okay? This is an analytical model. This is Jorge Peñarubia's idealized n-body experiment, where what he did is he takes an n-body subhalo which he evolves along an orbit in a fixed analytical host halo potential. And you see the same thing. The mass just undergoes these little steps every time you have a pericentric passage. Okay? So this is what we expect that should happen. What does the Bolshoi simulation look like? Here's the answer. These are 6 randomly selected, and I swear to God, these are randomly selected halos. The only requirement that at accretion they need to have more than 15,000 particles, because it doesn't want to look at close to the 50 particle limit. No, these are well-resolved halos. Okay? 15,000 at accretion. This is time, this is mass. So I plot only 2 per panel to avoid overcrowding. Okay? Here is where they are host halos. Okay? So they're still growing in mass. Then they become a subhalo, and this is where I expect the staircase-like behavior. But I don't see staircase-like behavior. This is stock market behavior. Okay? Things go up and down and then go up. And there are episodes where the mass of the subhalo goes up by more than an order of magnitude in a very small time. And yeah, what physical mechanism can make the subhalo grow by a factor 10 in 100 megayears? And the answer is none. Okay? So this is a complete, this is something going wacko here. And this is state-of-the-art subhalo finder applied to a state-of-the-art cosmological high-resolution simulation. 15,000 particles in a subhalo. And you might argue, well, but it's always tricky to identify the outer boundary of a subhalo because it's in this overdense region, the halo, and you may not be able to see the outer boundary very well. If it was just a problem with identifying the outer boundary, then Vmax, the maximum circular velocity, which is sensitive to the inner part of the halo only, would not show that. But you see, even in Vmax, you see this up and down. To make it worse, here is actually a nice plot that summarizes how bad it is. This is, I went to all the subhalos, and every time step compute the mass of the subhalo at t plus delta t divided by the mass at t. And delta t here is only 42 megayears. Okay? The nice thing about Bolshoi is it has very good time resolution of the outputs. So 42 megayears apart. This is the distribution I get from that mass ratio. Okay, so this is mass loss at the negative end. Positive end is mass gain. If that staircase-like behavior was correct, I only should have mass loss. Instead, I have about as much mass gain as mass loss. This thing is almost symmetric. Right? So what I did is I took this part of the curve and I flipped it over as a dashed line here. You see how symmetric the damn thing is. So there is a little bit excess mass loss compared to mass gain. That's the actual physical thing of the thing losing mass. But it's superimposed on something dramatically noisy. And I think most likely this has to do with the unbinding criterion that was used by the subhalo finder. I don't think this is a problem of the simulation. I think it's a problem of the analysis of the simulation. But this is state of the art. This is what people do for a living. And it basically means that the mass or the maximum circular velocity of a halo are basically good random variables. You want to make a random variable generator, just use the mass or the maximum circular velocity of a subhalo. This is bad. Statistically, things are converged, correct. But if you want to use individual masses and instantaneous masses, you have to be careful. What about disruption? It turns out that in these simulations, subhalos disrupt by the bushes. Show you. So I wanted to understand the demographics of subhalo disruption. So what I did is I identified all the subhalos at time step before they disappear from the catalog and disappear for good. Okay? They disrupt. And what I'm doing here is I plot the distribution of the instantaneous radii of subhalos at disruption compared in red to all subhalos. So disruption clearly preferentially occurs very close in, typically at about 10% of the viriradii, much closer than an average subhalo. That makes sense. That's where the tidal field is strongest. That's where you get your tidal shocks. You can look at the orbital circularity here. Okay? 0 is a radial orbit, 1 is a circular orbit. You clearly see that the things that disrupt are much more preferentially on radial orbits compared to the average. Okay? Again, it makes sense. Those are the things that get a larger tidal shock, that get closer to the center. Here's a distribution of the accretion redshifts, which is actually interesting. You see that the subhalos that disrupt are sort of bimodal in the accretion redshift. There's this pronounced peak at an accretion redshift of 0.15. Turns out those are halos, subhalos that accrete at that redshift, 0.15. They, by redshift 0, are experiencing their first pericentric passage. Okay? They get closer to the center. But what this then means is that a significant fraction of subhalos disrupt at their first pericentric passage before they have experienced any prior tidal heating or shocking. That already is puzzling. The most puzzling aspect, though, is this one. So this is the distribution of the masses of the subhalos at disruption, but expressed in terms of the number of particles in the subhalos at disruption. So here's this 50 particle limit. I don't do anything with subhalos below that because that's where the mass functions don't converge. Okay? And if you look, the thing that really surprised me, I expected to see disruption close to that mass limit of 50 particles. But clearly, the things that disrupt have the same mass distribution. In anything, they're a little bit more massive even than the average subhalo. There are subhalos there that have 10 to the 4 particles that are happily trotting along, la 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 la, boom, they're gone. 42 megayears later, they're gone, at least from the halo catalog. And you go, what is this? What is causing this kind of disruption? To show you how much disruption there is, okay, this is from a paper with Arthur. This is the surviving fraction of subhalos as function of their accretion redshift. And just look at the black line. If you go to a redshift 1, that's about here, you see that about 35% survive. It means 65% of all subhalos that were accreted at a redshift of 1 are gone, are disrupted by redshift 0. Okay? That implies a fractional disruption rate of 13% of all subhalos get disrupted every gigayear. That's very dramatic. Okay? And the question is this real? Is it numerical? If it's real, then what is doing it? Okay? So let's ask the question, what can cause actual tidal disruption? Well, you might argue tidal stripping. You just strip mass off, and if you strip and you keep stripping, at some point you'll probably disrupt the thing. Okay? We'll check that in a minute. Then there's tidal heating. Okay? So whenever a subhalo has a pericentric high-speed passage, goes with high speed, it undergoes an impulsive shock. Okay? It's like an impulsive high-speed encounter with the center of the host halo, and that dumps energy into my subhalo. And that will typically cause the subhalo to puff up and become more susceptible to disruption. Not only at pericentric passes, the same thing happens when I have a subhalo encountering another subhalo, which actually happens quite often. So that could be the dominant mechanism that causes disruption. Then there is dynamical friction. Subhalos sink to the center. The more massive ones will experience dynamical friction and will sink to the center and sort of blend in or merge with the background, not necessarily disrupt. And finally, of course, you always have to be sensitive, careful about numerical overmerging. So the question is, which of these is causing all the disruption in the simulations? Well, let's start and look at tidal stripping. And ask, can tidal stripping cause disruption of subhalos, complete disruption? And I came across this paper by Hayashi, which is actually quoted a lot. And they actually pointed out something really interesting. If you take an NFW halo and you instantaneously remove the outer layers down to about 0.77 times the scale length of the halo, then the remnant, the central remnant that remains, has a positive binding energy. You're like, really? You can actually calculate it, and it's true. You take an isotropic NFW halo, you calculate the mass of the inner region after you take off all the mass on the outside, that thing has positive binding energy. So Hayashi then argues, so once I strip down to that radius, 0.77 RS, which basically means you have to remove about 92% of the mass, you're left with something with positive binding energy that will just disintegrate by itself. Okay? Well, let's test that. It's simple to do, a simulation. Okay? So here's a simulation. Here is the original NFW halo, okay? But I've stripped instantaneously everything down to this little radius here, which corresponds to 0.67 times RS, so inside that radius. And you can verify for yourself, indeed, yes, the total binding energy of this stuff is positive. Okay, so let's run it. So here's a zoom in on the center. Here you see the original NFW profile. In black is what is, I've stripped it off here at the green line. And here you see the radial velocity dispersion. This is the radial profile of the density profile. The density of particles in here. Okay, so this is the embodied, so this is the radial density profile, function of radius, density, okay, and this is the radial velocity dispersion profile. I have done that instantaneous. I'm not saying that nature doesn't. We'll come back to nature in a second. This is idealized. Okay, so this is the maximum you can do, or the fastest you can do. Let's put it that way. Okay, so let's go. Here we go. Whoop. If you paid close attention, you saw a bunch of black particles stream out. Those were unbound particles. They're always color-coded black. Okay, and then after that, not much happens. Basically, the density profile becomes a bit steeper. Okay, it re-virializes and makes a nice virialized system. Velocity dispersion, and this I can run this for 200 gigayears and nothing happens. It just sits there nice and stable. And the reason why this total binding energy being positive doesn't disrupt the system is that there is a huge distribution of binding energies for the individual particles. And yes, there's going to be a bunch of particles that have very positive binding energies. Those are the particles that happen to be close at pericentric passage when I strip all the matter outside away. So they come out and go like, suddenly they don't see the outer mass anymore and they just take off. Adios, bye-bye, never to be seen again. But all the other particles nicely sit there, have negative binding energy, and they just rebind and make a new virialized system. And you can do this truncation down to much, much smaller radii. So what is plotted here is the bound fraction as function of this truncation radius in units of the scale radius. Okay, so this is that 0.77. Inside here, you instantaneously have a positive binding energy. The green curve is just the mass inside this truncation radius in the original NFW halo. Okay. And then after simulating, you get the red curves, so you get the blue ones, you get the red dots. Okay. So there's a little bit of difference. That's the mass that streams out, that's unbound. But then the system re-virializes and creates a bound thing. And no matter how far I cut it, I never disrupt the system. So the answer is, can stripping cause disruption? The answer is, at least in this picture, no. But let's go to the more realistic picture. Let's actually put something on a real orbit. Now, I want to start with simple things, one step at a time. So I'm going to put it on a circular orbit. Okay, so I'm having an analytical host halo, an n-body subhalo, and I'm going to put it on a circular orbit. Not because circular orbits are the most realistic, but because along a circular orbit I have no impulsive tidal heating. I have a fixed tidal field. So that's easier. In addition, I'm having an analytical host halo. I have no dynamical friction. Okay, so it's just tidal stripping. Okay. So what are we to expect is going to happen? Well, very naive prediction would be, well, you can calculate. Yes, host halo is not growing, fixed. Okay. So you can calculate the tidal radius. Okay. You can say, oh, all the mass outside of the tidal radius will be stripped off over time. Okay, so here we go. Okay. And this would be a very naive prediction, because clearly that can't be the solution, because there's going to be particles here that have orbits that have an epicenter that lies outside of RT. So they should also be stripped up over time. So a more sophisticated prediction, if you like, is that all the mass with an epicenter outside of RT will be stripped off over time. So let's see what happens in the simulation. So here we go. Circular orbit, subhalo, same as before. Let it go. Boof. You see all the mass being stripped out beautifully, creating a leading and a trailing tail. They phase mix out into beautiful rings, and the dark matter subhalo remnant moves in between these two rings. Okay. The thing is very cold, the remnant. Okay. The velocity dispersion, the density profile in the center has barely changed at all. Okay. And it survives and it survives. And you see also, interestingly, that it has moved away from its original circular orbit. It has actually moved in a little bit. And that's due to the dynamical friction. Not against the host halo, because that's not included, but against its own tidally stripped material. That actually causes the dynamical friction, which is actually not negligible. We'll see in a second. The upshot is here, 25 gigayears later, okay, 2 times the Hubble time, nothing really happened. Subhalo is still there. Okay. We can plot the bound fraction as function of time, shown here. Okay. And now let's compare this to these predictions. Okay. So if only the mass outside of the tidal radius in the beginning would have been stripped off, the thing would have sort of asymptoted out to here. Well, clearly there's much more stripping than that. What about the mass of all the particles with an epicenter outside of RT? Well, that would asymptote to here. There's even more stripping than that. Why? Well, the answer is simple. This is to do with feedback loops. once you take your halo and you strip mass of it, what you're left with is something that's unvirialized. It will go, oh, damn, I got to revirialize. It's going to redistribute its energies among kinetic and potential energies, and it always ends up puffing up. It means the density goes down, the system puffs up. That means the tidal radius moves in. That means now new mass lies outside of the tidal radius. It gets stripped off, mass loss, revirialized, da-da-da. This is a positive feedback loop, but it keeps going. In addition, a second order effect, the mass loss causes dynamical friction. The dynamical friction causes the orbit to shrink. You go to where the tidal field is stronger, tidal radius shrinks, you have more mass loss. Because of these two loops, you never sort of stop losing mass. You can clearly see that this thing, after 50 gigayears, it's still losing mass, albeit at a low rate. But it didn't disrupt. And here comes the problem. This part we can't treat analytically. We don't know from first principles to calculate, once I strip off some mass, what is the density profile of the system going to be after it revirializes. We can't calculate that. People have tried things with assuming adiabatic invariance and stuff, but it's only approximate at best. This is not something that we can analytically predict, and therefore I cannot make an analytical prediction of what this should be. And all I can do is I can compare a simulation to a simulation and hope that at some point I learn something. So that's what I spent the last year doing. I ran 1,200 simulations of subhalos on circular orbits only. And let me share you what I learned from that. So this is the bound fraction. Here we're actually varying a physical parameter, okay? Namely the orbit, the circular orbit. Okay, so this is at a virial radius. Okay, subhalo loses a little bit of mass. If I make the orbit smaller and smaller and smaller, here's 0.15 times the virial radius, and then I went to 0.1, and suddenly, hey, it suddenly went, joof, turned over, and it disrupted. And I was very excited. I was like, yes, I see disruption. Now I can go and probe and figure out what's going on. Okay. So for reasons that I don't even recall, I decided to take this simulation, 0.15, and run it 10 times with 10 different random realizations. So what does a random realization mean? It means that whenever I set up the initial conditions, right, I have to draw positions and velocities from an energy distribution function, and that's a random process. Right? So I can do that 10 times, 10 different times, 10 different random realizations. And running these different random realizations should be the same as running a simulation on Monday or Tuesday, right? Should not make a difference. Well, here's what I got. 10 different simulations. These have 10 to the 5 particles each, okay? Not 100 or 50 or 1,000, 100,000 particles each. Okay? Here they go. And in some case, this particular case turns out to be an outlier, it survived for 60 gigayears. And in some cases, it just, poof, after 12 gigayears, disrupts. At their half mass radius, it's going to be 2 gigayears. Mm-hmm. Yeah, here 10 to the minus 2. Mm-hmm. Mm-hmm. Yeah. Yes. And you think, and so that's exactly where I went. I was like, this is two-Wood-relaxation effect that's screwing me up. So, many hours later, no, it's not two-Wood relaxation. Turns out you can actually test this. I can pump energy into these systems. I can disturb them. It doesn't do anything. What is going on is actually discreteness noise. It is pure discreteness noise effect. If you have a halo and there's this tidal radius, there's only going to be particles that move at any moment in time. There's going to be a bunch of particles that move across my tidal radius. And that number is subject to Poisson noise. And normally in a halo in isolation, you have a bunch of particles and they will come back over time and nothing happens and that phase mixes out and you're happy. But now a few particles go across and they get stripped off. So if you now have a fluctuation that fluctuates high, you have a high fluctuation in the mass loss rate. So now the system revirializes a little bit more than average. It puffs up a little bit more than average. The tidal radius moves in a little bit further than average. And the next time, so I lose even more mass. So what you actually get is you get discreteness noise amplification because you're in a tidal field. That's what's causing this. We have tested this in great detail. You can show it has exactly the Poisson behavior. Yes?
In the upper panel, it's all the same subhalo.
Yeah. Correct. Correct. Yep. So it's only once you actually do the different random realization that you suddenly see that. So it turns out this is discreteness noise. And the only way to beat down discreteness noise is increase n. Okay? So we'll do that in a minute. But first I wanted to point out another problem. The other problem has to do with softening. So why do we soften particles in a simulation? It's because what we really want to simulate is dark matter particles. And two dark matter particles have very little mass, and when they move next to each other, they just go, they don't feel each other's perturbance. But we're modeling them by particles that have 10 to the 8 solar masses. So 10 to the 8 solar mass particles come next to each other and they go, vroom. You get these huge, large angle deflections. That's not physical. So what you do is you replace your point particles with fluffy blobs. And now these 10 to the 8 blobs go straight. So the dynamics, that's what it should do. How do you determine how big your softening length is? Well, if you make your softening very large, whoops, that's not good. If you make your softening length very large, okay, then your blobs are nice and big and they will move through each other and you get the dynamics right. But now, if you try to resolve a high steep cusp in the dark matter, all your particles are fluffy blobs like this, you can't resolve that cusp. And you make your entire system fluffier than it really is. Okay, so that's what is shown here. This is plotting the number of particles inside a certain radius, okay, as function of time in a simulation. The dotted lines is the analytical answer. That's the system I want to simulate. Okay, an NFW profile, and I want basically these lines here to lie on those dotted curves. If I make my softening length very large, this is 0.25 times the scale length. Remember Klippen saying between 0.1 and 0.3, so that's okay. Okay, what happens is you're going to be, if I run the simulation, these number of particles within a fixed radius stays perfectly the same. That's good news. It means my system is stable. Okay, I want my system to be stable. But it is not lying on the dotted line. Okay, I'm systematically doing something wrong, and that's shown here in the density profile. This is the density profile I want to model, but because my softening length is so large, I'm actually making something that has a much lower central density. Okay. Now, what happens if I make my softening length very, very small? Well, now I'm back to the problem that I have these large angle deflections. And what happens is you get two virialization effects. So now initially, I'm actually making the system that I want. My curve lies right on the dotted line, but it moves away. It evolves due to two-body virialization. And two-body virialization makes a beautiful isothermal core. Okay, density core, isothermal. So that's not good either. So what you do is you go and find something in between. Okay, you compromise. And in this case, you find that the softening length of 0.05 for 10 to the 5 particles is what you want. You see you're almost on the dotted line. You're almost constant with time. After 60 gigayear, the velocity dispersion profile and the density profile is still pretty damn good. This is the best you can do with 10 to the 5 particles. And this is what people normally do. This is how they determine optimal softening lengths. There have been papers written how you compute that. Okay, very nice paper by Walter Danen. You should all read it. So this is what you normally do. Now, what do you expect if you're going to put these things in a tidal field? Okay, suppose I take this one and put it in a tidal field. My halo is too fluffy, so it will be too easy to disrupt it. So this one is probably going to make the system lose more mass than this one. What if I go and make my softening length too small? Same thing. I make a core. I should be more disruptible, and I should lose more mass. So the prediction is, for this system, I should get the most bound mass over time, okay? The least amount of stripping. Unfortunately, that's not what happens. If you do the simulation, here you see the results, the bound fraction as function of time. In black is this 0.05, that's the optimal softening length. This is for 3 different radii. Just focus, for example, at the middle panel here. If you go to the red curves, you make your softening length larger. Indeed, as expected, you start to lose more mass. You disrupt more quickly. But surprisingly, if you go to smaller softening length, you don't also go in that direction. You actually survive more and more. And you don't disrupt. In fact, if I go to a softening length of 0.01, in all cases, I survive. And the reason is the following. It turns out that the optimal softening length scales with the size of your system and the number of particles that you use to resolve it. But that is changing if you're a subhalo and you lose mass. So what you can do is you can actually calculate what is this optimal softening length as function of time. And that's what is plotted here. And you see it starts out at 0.05 and then boom, it drops like a rock and it sort of saturates out at 0.01, 0.02 in all cases. And if you actually run it with a softening length of 0.01, 0.02, they all survive. You don't get disruption. So the upshot is the optimal softening length that people calculate for isolated halos is not applicable in a tidal field. In a tidal field, you want to run a smaller softening length. So now we're left with two problems. We have a discreteness noise issue and we have a softening issue. And the question is, but what is the right answer? And we ran simulations where we went to larger n, smaller softening length, ran 10 realizations for each case to see that we don't have discreteness issues. And we finally converged. But for this radius of 10%, which is the typical radius where these subhalos and Bosch disrupt, remember, I need 10 to the 7 particles and a softening length of 0.003. That's in units of the scale length of the NFW halo. That's tiny. And then I get this black curve, and it survives. And now in each panel, I change the number of particles in the subhalo from 1 million, 300,000, 30,000, and I change the softening length. And each panel you see 10 blue curves, which are 10 random realizations. Okay? And the red line is the average from those 10. And you can see that if you want to resolve this system properly, the dynamics, you need to be roughly here. 1 million particles, softening to 0.003. You start to see some dispersion among the 10 different random realizations, but after a Hubble time, it's still about 0.1 dex. I can live with that. But anything else? Garbage. Now look at this discreteness noise. It's unbelievable. This is with 1 million particles, 300,000 particles. If you make a softening too large, every time, you get disruption. It's completely artificial. To put this in perspective, the best resolved subhalo in the Bolshoi simulation has about 30,000 particles at infall, is resolved with a softening length of typically 0.2-ish. So that sits about here. We're way off from what is required to resolve this dynamics. Better yet, if these people say, oh, let's do a resolution study. So let's go and be bold and let's run it with 10 times as many particles. They never do that, they do 3 times. 10 times as many particles. All right, we'll go to 300,000. Let's make the softening length a bit smaller because I have more particles. We'll go here. And you come at this to this and you go, yeah, I'm converged. Yeah, you converged, but not to the right answer. Okay? You have to be way off. It's not as bad as that because it depends on where I do my integration. If I integrate at half the virial radius, you can actually get away with much fewer particles. 10,000 particles is perfectly fine. Okay, you have to be careful. Sometimes you get two-body virialization effects. This actually is two-body virialization. But so the problem is that now the requirements for what you need to do with your simulation depends on the tidal field strength. Oh God. But so far, I've only done circular orbits. I ran 1,200 simulations of circular orbits. Okay, that's what you do when you're tenured. So the question is, but you have not included any tidal heating. And most orbits are eccentric. And then you get tidal shocks. That must cause disruption, right? Well, let's see. What do we expect? What do we expect? In order to work out what we expect, what I did is I went to Bolshoi and I identified all the subhalos at accretion. And for each subhalo, I measured the orbital energy and the circularity. So I now know what the orbit that subhalo is going to be on. And then I integrate that orbit. And along the orbit, I apply the impulse approximation to work out how much tidal heating it gets, using the model worked out here in Princeton by Oleg and Jerry. Okay, it's a beautiful model, very accurately. They've tested it in great detail. And you can calculate how much energy is pumped into my subhalo due to the tidal shock that it experienced at pericenter. And I compute that for one orbit. And then I compare that to the total energy, binding energy of my subhalo. And this is what you get. This is the distribution you get. This is in the log of delta E over E tot. Okay. This is 0, so that corresponds to 1. So if you're in this red zone here, it means that the energy that is pumped into the subhalo, just due to one pericentric passage shock, is larger than the binding energy of the subhalo. And what many people do is they say, that means that's disruption. But that would mean that 80% of all subhalos would disrupt at the first pericentric passage. That's much more than what you see in Bolshoi. It's only a few percent. 80%. That means none of this, there would be no substructure. Okay? And the reason is that this is not what you want to do. Because just calculating how much energy you pump into the system doesn't tell me anything about how that energy is distributed over the particles. And that's what's important. So what you need to do is you need to compute for each particle how much energy does that particle get and how does it compare to the particle's binding energy. And if you do that, you can do that by making a Monte Carlo realization of that halo and integrating along the orbit, calculating it for each particle. And then I compute the bound fraction as a fraction of particles for which its delta E is less than its own binding energy. those that get a delta E larger than binding energy, they will get a kinetic push that is large enough so they can escape. Okay? And then you get this is a corresponding bound fraction that you compute. Most of them only lose about 20% of their mass. In fact, you can calculate that I can dump 100 times the total binding energy into my subhalo, and I only strip off 85%. 15% remains bound. Partly that's because the central region is actually adiabatically shielded from an impulse approximation, from an impulse, because there the orbital time is very short. For them, pericentric passage is just an adiabatic event and not impulsive. So based on this, you don't do much damage with tidal heating. Okay? And you can actually compare it. Okay, so the upshot is, don't use this to judge whether something will disrupt or not. Okay? That's a very bad thing to do. Here we actually compare for individual particles the initial energy to the final energy for a particular case. And you see if you lie above 0 here, it means you're unbound. So there's a lot of particles that become unbound. Okay? This is for a particular orbit. This thing actually goes up all the way to very large values. Okay? So a lot of that large amount of energy goes to a few particles that get way more energy than they need to escape. And then what I did is I color-coded them according to where they are at pericentric passage. Are they outside the tidal radius or inside the tidal radius? And you see that all these particles that get stripped off because of the energy that are dumped in, anyways, lies outside of the tidal radius. Even if I did not put in any energy, these particles would anyway be stripped off. In fact, there would be more particles stripped off just because of the tidal field than because of tidal heating. So I can plot that here. This is as a function of the orbital circularity, right? So 0 is a radial orbit, circular orbit. This is the bound fraction after one orbit if there would just be tidal heating. You just dump that energy in, okay? And the dashed line is if you ignore the adiabatic correction. Well, you see that doesn't make much difference. But you can also ask what fraction gets stripped off or will remain bound just because of the tides are outside of RT. That's the purple line. That lays way below. So you strip off way more particles just because of the tide than because of the tidal heating. Okay, and if you take into account that it's actually the epicenter thing, then it's even lower. So the upshot is tidal stripping completely dominates over impulsive tidal heating, and tidal heating doesn't do much. And we have run now a whole bunch of eccentric orbits, and if you go to 10 to the 7 particles, a small enough softening length, I can make them go right through the center, and they'll go on happily living forever, and they don't disrupt. So I don't get any disruption. So what if, indeed, all disruption is artificial? Let's entertain that thought for a minute. I don't think that's correct. I think there's actual disruption in that there are halos that are massive, that experience dynamical friction, and they go, they don't really disrupt, they just merge and blend in against the background. They come to rest in the center. They lose their identity, but they don't necessarily disrupt. So if all disruption is real, we can make a very quick estimate of what happens using an analytical model that I developed with Arthur as part of his thesis. Arthur developed as part of his thesis, I should say. So what we did there is we have this merger tree. We know when halos accrete, and then we have a model for the mass stripping as the halo orbits around, and then we included disruption. Now, we had no clue how to model disruption because we didn't understand it. So what we did is we just went to the Bolshoi simulation, looked at the demographics of when do subhalos disrupt, and put that into the model so that we can reproduce Bolshoi. Okay, so it's not much of a model, but we could reproduce Bolshoi. So here it is. This is the mass function of Bolshoi halos in red, and our model is the gray curve. For comparison, this is the unevolved subhalo mass function. That's the mass function of all things you accreted over your entire life. Everything you ever accreted, which is a universal function, interestingly enough, but that's another story. The open circles are the masses at accretion of the subhalos that survive to the present day. Okay? And those are the circles. So the difference between the blue and the open circles, that is due to disruption, which is dramatic. The difference between the open circles and the solid circles, that's due to mass stripping. Okay? So the upshot is we can reproduce every aspect of the model, also the Vmax function, the mass over mass accretion distribution. This model was tuned to do that, to reproduce Bolshoi. But now the cool thing is I can say, let's just turn off disruption. Turn it off and see what happens. This is what happens. This is the actual mass function in Bolshoi. This is now the prediction without disruption. And basically at every mass scale, I move up by a factor 2. Okay, I don't just change things at a low mass end. No, remember, disruption in bolstering happened at every masses, and the entire mass function goes up by a factor 2. If this is the real answer, and this is what the simulations tell us, then we're underestimating the number of satellite galaxies all the time by a factor of 2. The boost factor of dark matter annihilation is underestimated by a factor 2. Not that that matters too much because the uncertainty there is a factor 1,000. But this is huge for small-scale clustering. In fact, in subhalo abundance matching, there is a problem. If you just abundance match onto the mass of a halo, okay, you assume there is a relation between mass and stellar mass, halo mass and stellar mass, you underpredict the clustering on small scales quite dramatically. How do people solve that? By assuming that the stellar mass abundance matches to V peak, the maximum circular velocity that the halo ever reached over its life. Turns out that that's actually a fairly stochastic variable, which has to do with when did the halo have its last major merger. And you go like, why would that be? It makes no sense. But if all subhalos are just underestimated by a factor 2, there's twice as many subhalos, this problem completely goes away, and I can perfectly reproduce the clustering by just doing abundance matching onto halo mass. So that's a separate story, but it shows you how important this effect may be. So let me conclude. Abundance and demographics of dark matter substructure is important for a wide variety of astrophysical applications. In the current simulations, there is prevalent subhalo disruption, but what causes it? I think the only physical disruption that might be there is dynamical friction, but anything else, I'm pretty convinced now, is just numerical, partly due to inadequate force resolution, your softening being too large, discreteness noise that gets amplified in the presence of a tidal field. The only way to get around that is large n, much, much larger, so don't use subhalos with 1,000 particles, 10 to the 7 particles. Okay? Small softening length, much smaller than what you calculate for isolated halos. Okay? Tidal heating is subdominant to tidal stripping. And here's the main thing, this current generation of cosmological simulations, okay, still suffers from severe overmerging. And this is a serious roadblock to all this small-scale cosmology program. If we're going to use in any data out of LSST and DESI and all these things, not on large scales but on small scales, we better solve this issue first. Okay, it's also for understanding galaxy formation, near-field cosmology, the stripping and the streams of halos. If we can't even trust the dynamics of the simulations there, this entire program is at risk. So how do we proceed? Well, ideally, you just go larger n simulations, just wait for Moore's law to continue, and then at some point we'll get there. But then you need to use an adaptive softening. That's tricky in itself, because it has a tendency to break can't think of the word, symplecticity of your integrator. But people have found ways around that. There's actually some very nice work where people have used adaptive softening, but adaptive to the local density, to a local parameter. That's quite easy to implement in a simulation. But what we need here is adaptive to the tidal field over the subhalo. That's no longer a perfectly local variable. That makes, the computational cost will be enormous to do that properly. So rather, I think what we're currently doing is we're characterizing the shortcomings of n-body simulations. We're integrating these 10 to the 7 solar mass halos, huge parameter space of orbits and mass ratios and concentration ratios, in the hope that that will allow us to make at least some correction to the cosmological simulations. Okay. It's not ideal, but I don't know of any better way of doing this. Thank you.